Alrighty, let us get started. So today what we'd like to do is look at a second version of a truss analysis, which is called the method of sections. So before we've learned the method of joints, which if you have some, let's say truss like this, of course, don't mind my bad drawings here, I'm just drawing it quickly, but you could have a truss, something like this, with some set of loads, and we have different joints, and we'd like to know what is the force running through each of these members, A, B, C, D, E, F, G, H, and whether those forces are tension forces or compression forces. And we know how to do this by the method of joints, which is, number one, you do global equilibrium. That allows you to find the reactions at the supports. And then from there, you would look at each joint individually. And for each joint, you would do the sum of the forces in X and the sum of the forces in Y equal to 0, because, of course, we should have all of our forces equal to 0. This is the statics case, right? We don't want our truss to be moving left to right or up and down. We want it to be static. So at each joint, all of the forces should be in equilibrium. They should be equal to 0. Now this time what we'd like to do with the method of sections is slightly different. For the method of sections, what we're going to do is we're going to solve for the force running through several members, magnitude and direction. We want to know, of course, how much force. We want to know if it's in tension or compression. But with the method of sections, instead of trying to find the force in every single member, the method of sections, generally speaking, is all about finding particular members. So instead of finding all of them, maybe we only want to find 2 or 3. You know, we're interested in one particular part, so maybe we want to know this member, and this member, how much force is running through those 3 members. And we don't really care about the rest of them. Well, the method of sections allows you to find this much quicker than you would if you had to do the method of joints, because of the method of joints, you're finding the force in every single member. And so that's a lot more work. If all you care about is only 3 of the members, why are you looking for the force through all the other ones? So the method of sections allows you to solve this kind of a problem much more quickly. However, the disadvantage is you're only finding the forces through those particular members, and those particular members have to be related in some way. So for instance, it's not just that any 3 members I could find using the method of sections, but rather 3 particular members that are pretty close to each other, and I'll tell you why in a second. So the method of sections is just a different way of analyzing a particular structure, a truss in this case, where we don't want to know all the information. We only need to know some of the information, and thus we could use kind of like a shortcut method, and that's what the method of sections is going to be for us. So let's go ahead and figure out how this particular member or method happens to work. So let's say, I'll go ahead and erase this and make a better version of this particular truss. Let's say we have this truss, for instance. Here it is here. Here's our truss. Okay, and we have it look like this. Here we have our pin support. Here we have a roller support. Call this A, B, C, D, E, F, G, H. Those are our pins. And let us say we have a set of loads. Let's say 100 here, maybe 200 here, 100 here. And then let's give it some dimensions. Let's say each of these in the horizontal direction are 3 meters. And maybe the vertical dimension will be 4 meters, something like this. And let's say this time our question is asking us to find the force in members CD, DG, and FG. So this problem is asking us, we only care about these 3 members. For whatever reason, maybe we are reanalyzing something that's already been built, or maybe we're kind of trying to figure out what kind of material we should use for this part of our truss. We know what's going on with the rest of it, but this particular part, for whatever reason, we need to analyze again. Maybe we've discovered there's some issue going on. Maybe we did an experiment and things are falling, things are breaking on this side of our truss. So let's figure out what's going on over here. And if we look, those particular members, here's CD here, here's DG here, and here's FG here. So we have these 3 members we care about. Okay. Now, the first thing to note is the method of sections at most allows you to solve for 3 unknown members. Okay. Why is this? Because just as is true with the rest of statics, we only have 3 equations. The only equations we have are the sum of the moments equals 0, because of course we don't want our truss to rotate. The sum of the forces in the x direction is equal to 0, because we don't want our truss moving left and right. And the sum of the forces in the y direction is equal to 0, because we don't want our truss moving up and down. So if we only have 3 static equations, 3 limits to our truss, then we at most have 3 unknowns we could solve for. This is just a truism of mathematics. Math says that the number of knowns you have tells you the number of equations you must have. If you need 2 unknowns, you're looking for x and y, you better have 2 equations. If you have fewer than 2 equations, it's an impossible problem to solve. And then there's also issues if you have too many equations. If you have way more equations than unknowns, then you have too much stuff, and thus you won't get proper answers. We need the same number of equations as unknowns. Thus, if all we have are 3 equations to work with in the general principle, then at most we have 3 unknowns we could solve for. So if you're given a problem on a test, you're given a problem on a quiz or homework or whatever, and it's asking you for 3 particular members, that's telling you right up front, use the method of sections. If instead we're looking for we're looking to just analyze a truss, we want to know how much force is running through all the members, then we have to rely on the method of joints. But for the method of sections, we can find out 3 particular unknowns. The other thing to note is that for this to work well, those 3 members that we're interested in, you have to be able to connect them with a single cut, as we'll see, a single line. We have to be able to draw through all 3 members without going through a 4th or a 5th or a 6th or whatnot. So for instance, I could not have a truss like this, let's say, and I want to know what is this member, and this member. That's 3 members I want to know the unknowns for, but as we will see, the way the method of sections happens to work, I would not be able to use the method of sections for this particular problem. We will find out that the 3 members you have to work with have to be close together, connected in some way, as we will see, so that this particular method will work. Okay? All right, so let's figure out how the method of sections work. First step. Once we know we have to analyze a truss, it doesn't matter how we do it, whether it's the method of joints or the method of sections. The very first step is always the same: global equilibrium. That is to say, we need to figure out what is the reaction at the supports. Okay? And to do that, we use global equilibrium. That's the first step. So let's go ahead and do it. Let me redraw my truss here. I'll go ahead and pause it. Okay. So here I've redrawn the truss. We want to do global equilibrium. What does that mean? That means at the supports, depending on the type of support, there's going to be some reactions. Because of course, if this truss has a load acting on it, that load is trying to move the truss. Maybe it's trying to pull it down or move it to the right or whatever it's trying to do. And those supports are trying to keep it in place. It's trying to stop it from moving. So those supports are going to react to the load to try to stop the truss from moving. So we know for the pin support at A, a pin support allows for two different reactions, one that's perpendicular, one that's horizontal, or one that's parallel to the surface. Okay? So in this case, the surface is horizontal, so there could be an AY, I'm going to assume it's upwards, and there could be an AX, I'm going to assume it's to the right. Now again, as is true for method of joints, or when we're just calculating reactions on its own, you could just guess a particular direction for these reactions, maybe up, maybe down, maybe left, maybe right, I don't know. You guess, and then if you happen to be wrong, if you guessed up but the reaction is actually down, the only difference is when you get your answer, the answer is going to be negative. So you know, oh, it's negative, that means I thought it was up, it's actually down, or I thought it was down, it's actually up. So you just change the direction and you make it positive again. Thankfully, the number itself, the magnitude of the reaction, you'll still get the right answer. It's just a matter of, is the direction correct or not? And you just guess. Either you try to figure it out from logic. In this case, I see all the loads are downwards, so I'm assuming the supports are going to be upwards reactions. So I would say at A and at E, both reactions are going to be up. I might be wrong, but I'm guessing that by logic. If you don't want to try to think about it, maybe we have a truss that's not as simple as this one. There's a whole bunch of loads in all sorts of different directions. You may not be able to guess whether the the reaction is to the left or to the right or whatnot. So you just guess a direction. Usually what the guess is, if you don't know or if you can't tell by looking at the picture, usually engineers will guess them to be in tension. Tension meaning away from the joint. And then if you happen to get a negative, oh shoot, it was compression actually. It's going the other way. That's fine. But if you can guess it, it's best to try to guess it. In this case, I'm going to guess for A, the pin, two reactions, a horizontal and a vertical in this case. That is perpendicular to the surface and parallel to the surface. I'm going to guess the vertical reaction is up and the horizontal is to the right. And then at E, I'm going to guess, because it's a roller, it's only a perpendicular reaction, I'm going to guess it's upwards, EY. All right, but that's just my guess. It doesn't matter. I could have guessed the other way. It's fine. Once I've guessed my directions for the two reactions, I now use my global equilibrium equations, and I've got three of them. The moments better be zero, the forces better be zero in X, and the forces better be zero in Y, because this is statics. Things are not moving, thus the sum of the forces better be zero in all directions, and the sum of the moments better be zero, so there's no rotations. As is usually the case, when you do the sum of the moments, that's the first reaction equation you should always use, and you should always find the sum of the moments with respect to the point which has the most number of unknowns. You're always allowed to find the sum of the moments about any joint, about any point on your truss. It doesn't matter. But the point is you're trying to find the sum of the moments about a point where most of your unknowns go away, so you only have one unknown left in your equation. For instance, and we've done this with the reaction before, but just to review, if I tried to do the sum of the the sum of the moments at E, notice I'm going to have an AY and an AX, two unknowns in my equation, two unknowns in a single equation I can't solve. However, if I do the sum of the moments about A, the AY and AX unknowns go away because there's no moment due to forces at the point of rotation. So the first reaction equation I'm going to use is the sum of the moments about A is equal to 0. What do we have? Well, we've got the 100 force pulling down. That's going to cause a rotation. Its distance away is 3 meters from the point of rotation. That force tries to make my truss rotate clockwise, and clockwise rotations are always negative in physics, so that moment is negative. Then I have a 200 Newton force at a distance of 6 meters away from A. He's also trying to make the truss go clockwise. And I've got a 100 Newton force at a distance of 9 away, also clockwise. And then I've got EY, my reaction at E, a distance of 12 away, but he tries to make my truss go counterclockwise, so he's a positive moment. Those are all the forces in my truss that give rise to moments, set equal to 0, and now I could solve for EY. So EY is equal to 300 plus 1200 plus 900, all divided by 12. That is 1200 plus 1200 is 2400 over 12. 12 cancels the 24, makes that a, I'm sorry, not a 12, a 2. So I get 200 for EY. Positive, I got a positive answer here. The positive answer does not tell me the direction. What it tells me is the direction I guessed is correct. In this case, I guessed EY to be upwards. Because I got a positive answer, that means the upwardsness is correct. So it is indeed up. So there's my first reaction. EY, the reaction at E, the roller, is 200 newtons in the upwards direction. All right, so that's my first reaction equation. Next, let's look at the sum of the forces in the x direction. That's equal to 0. What are all the x forces here? Well, I've got AX to the right, so positive AX, and that's it. There's no other horizontal force in this equation, in this truss, so AX is equal to 0. There we go. There is no horizontal reaction at A. Finally, the sum of the forces in the y direction better be equal to 0. All right, what are all of our y forces? Well, I've got AY upwards, so positive AY. Then I've got 100 down, so minus 100. Then I've got a 200 down, minus 200. Then I got another 100 down, minus 100. And then I've got EY up, so plus, and EY I already found was 200, so that's 200. Those are all the forces in the vertical direction acting on my truss, set equal to 0, so I get AY is 100 plus 200 plus 100 minus 200. So the 200s cancel, and I get AY is 200 newtons. Positive, which means the direction I guessed was correct. What direction did I guess? I guessed AY to be upwards, so it is indeed upwards. So AY is 200 as well. Of course it is. If we look at our truss, it's a nice symmetric truss. All the dimensions are symmetric. The load is symmetric. So, of course, the reaction at the supports are going to be symmetric as well. At E, it's 200 up, and at A, it's 200 up. Fine. But, of course, even if we didn't know that ahead of time, the mathematics gives us all the information. That's what's nice about this physics and engineering is, one, we can use logic and reason to try to figure out what we would expect the answers to look like. But even if we didn't want to go through the trouble, even if we wouldn't want to take the time to try to think about how the answer should look, the mathematics, as long as we're good with our math, we understand when's negative, when's positive, all this kind of stuff, the math will tell us everything. So if I had guessed AY to be downwards, I would have gotten 200 negative. Negative means the guess I made about its direction was wrong. It does not mean negative means downwards. Negative means whatever I guessed is the wrong way. I had guessed downwards, so it should actually be upwards. If I had guessed upwards and got negative 200, then I know, oh, my upwardsness was wrong. It should actually be down 200. Okay, so it's very important to note the difference between normal physics, which is everything that's up is always positive, everything that's down is always negative, just by standard notation. Here what we're saying is, yes, we're going to assume everything upwards is positive, everything downwards is negative, but when I get my answer, if I get a negative number, that doesn't mean the answer is downwards or leftwards. What it means is my guess was wrong, or my guess was correct if it was positive. Okay? In this case, I got two positive answers for E and A, which means I had guessed correctly, I had guessed upwards, so they are upwards. All right, that's just a review of reactions, but so far there has been no difference between what we've done in the past with method of joints and what we're doing now with method of sections. All we did was figure out the reactions at the supports. Now is where things change. So let me go ahead and rewrite the truss and start on the new stuff. All right. So here we have our truss redrawn, where now I've written in the reactions at the supports at A and E. In fact, let me make sure E looks okay here. All right, so there's my truss, and in yellow, I've again highlighted the particular member of interest we have for this problem. Here is where the method of sections diverges away from what we did with the method of joints. Because I want these yellow members here, I've drawn CD, DG, and FG. Method of sections says if you could break your truss into two different pieces by drawing a line or making a cut or breaking the members of interest, that's what you should do. So here, I want CD, DG, and FG, right? The yellow ones. Well, I can make a cut in my little truss here, right down that line there. And that's going to break my truss into two pieces. The first piece over here, okay, here it is. That's what it looks like. Here's the 200. Here's the 100. Here's the 200. And then this thing is called CD. This thing is called DG. And this thing was called FG. Right? So that's the left side. And then the right side looks like this. Here's the right side of the broken truss I've just created. Looks like this. So here's the 200 at E, here's the 100, and then this guy is CD, this guy is DG, and this guy is FG. Okay, and again, that's the interesting thing, The yellow pieces are the things I have interest in. So all I did was I broke my truss into two halves, or two pieces, they're not halves, by cutting the members of interest I have for my problem, and I just put one side on the left and one side on the right. So there's the two pieces. The method of sections says once you've broken it into your two pieces, choose one of the two pieces to work on. And in fact, of course, you want to choose the piece which is easiest to work with. That is, the piece that has the least number of things you have to worry about. Because what we're going to do is we're going to use our same three global equilibrium equations we did in the past, the reaction equations, sum of the moments and sum of the forces equal to 0, on these pieces. So we want to choose the piece that has the least number of forces in it, the least number of things to worry about, so that our equations become a little easier. However, it actually doesn't matter which piece you use. You can still get the right answer. It's just you want to choose the piece that's easier. That way you don't do more work than you have to. If both pieces are going to give you the same answer, but one piece has 1,000 forces on it, and the other piece only has 3 forces on it, well, why use the piece that has 1,000 forces? That's much more complicated, just to get the exact same answer as if you only looked at the piece that only had 3 forces on it. So when I look at these two pieces, the piece on the right is easier to me because I've got my 3 unknowns, the 3 yellow members I want, but it's only got 2 external forces, the 100 down and the 200 up at E. Whereas the piece on the left, again, has my 3 unknowns, the same 3, but that has 3 external forces, the 200 at A, and then a 100 at H and a 200 at G. So it's got one extra unknown, not unknown, it's got one extra external force, one extra load that we would have to keep track of. Not that big of a deal, only one extra force, who cares? But for more complicated problems, of course, one side of the truss may be way more complicated than another side. Here, I'm going to use the right side because it's the easier side. Once you know which side to use, what do? Step 2, do global equilibrium again. So sum of the moments, sum of the forces X, and sum of the forces Y, all equal to 0, on that piece. And that'll give you your 3 unknowns. That's why when you use method of sections, you better have 3 members of interest. If you have 5 members you're interested in, you can't just use method of sections. We only have 3 equations. So at most, we can solve for 3 unknowns. But that's what we have in this case. We want CD, DG, and FG. 3 unknowns, and we're going to use this right side. So again, let me redraw the right side on a new paper, and we'll start actually doing the work. So here it is. We've got this and this. Let's see, that is something like that. Okay. This is 100. This is 200. This is CD. This is DG. And this is FG, I believe. All right, so there is the piece of the truss that I'm going to work with. And now I have to use my 3 equations to solve for these 3 unknowns, CD, DG, and FG. Now the next step is, before I start doing these equations, I need to choose a direction for the forces for each of these 3 unknown members. Now, unlike with method of joints, where we would try to logically figure out what we think the direction should be, here, don't worry about it. Just always guess. We think the forces will always be in tension. So I'm just going to assume all of these 3 unknown members are all in tension. And if I get a negative answer, then I know, oh, it was actually compression. Also, remember this DG here being at an angle. If I look back at the dimensions, that angle is a 3, 4, 5 triangle style. So this is 3 and this is 4. And then we know from here to here is a 3, and from here to here is a 4, in terms of our dimensions. All right, so what do? First step, sum of the moments equal to 0. Now, we have several different places, here, here, or here. 3 different places we could choose to calculate the moments about. Again, just as is true when we find the reactions, the global equilibrium, you always want to choose that point which gets rid of most of your unknowns. So here, this top point, and I'll do it in red, this red point here has CD and DG on it. So if we choose that point as the sum of the moments, or to calculate the sum of the moments, then CD and DG, 2 of our 3 unknowns, will go away, because those 2 forces are acting at the point of rotation, and thus no moment for them. So the only unknown we're going to have is FG. Of course, we'll have other forces giving rise to moments, but we know those forces. What we don't know is FG. So I'm going to choose this red point as the point about which I calculate these moments, and that'll get rid of 2 of my 3 unknowns. So sum of the moments equals 0. What do we have? Well, we have the FG times, we need the perpendicular distance. FG is a horizontal force, so we need a vertical distance from FG up to that point of rotation, which is our 4. FG causes our truss, or this piece of our truss, to try to go clockwise, so he's going to be a negative moment. Next, we have this 100 here, but that 100, notice, his line of action, his force, lines up perfectly with the point of rotation we're talking about. So he will not give rise to any moment. So that 100 load does not give a moment, so I don't need him in this equation. We do have the 200, so we have the 200. He's a vertical force, so we need the perpendicular distance, which is a horizontal distance, which is 3 in this case. And this force tries to make our truss go counterclockwise, so he's positive. Okay? And then, of course, the CD and the DG, they're both at the point of rotation, so they give rise to no moment whatsoever. So these are the only forces that give rise to moments. Set it equal to 0, and we saw for FG, we had FG is equal to 600 over 4, which is 150. 150 positive. Positive means counterclockwise, or I should say, I'm sorry. Positive means the direction I chose was correct. I had chose tension for FG, so FG is indeed in tension. We've got one of our 3 unknowns finished. If this number had turned out to be negative, that tells me the guess I made about FG was wrong. I had guessed tension, so it must be compression. Or the other way around, if I had guessed compression and it was negative, then it's actually in tension. But here I got a positive answer, which means my guess was correct. In this case, the guess was away from the joint, and away from the joint means tension. So FG, there he is. Next, we have 2 more equations we could use. We have the sum of the forces in X is equal to 0, and we have the sum of the forces in Y is equal to 0. Which one do we want to use next? Well, as is always the case, you always use the equation that you can actually solve. So, for instance, if we look at the sum of the forces in X, what are all of our X forces? Well, there's an FG. I'll do it in green, FG. There's some piece of our DG, which is going to be in the X direction, and there's CD, which is in the X direction. Well, CD and DG are both unknowns. So if I tried to do the sum of the forces in the X direction, I would have 2 unknowns in that equation. I can't solve 2 unknowns with 1 equation. However, and now I'll do this in yellow, if I want all the Y forces, well, there's the 100, there's the 200, and then there's the piece of DG, which is in the Y direction, and that's it. Notice CD is horizontal. So in the y direction, the only unknown I would have is the y component of dg. That's solvable. So I'll do the sum of the forces in the y direction first. What are all the y forces? Well, I've got the 100 down, I've got the 200 up, and I've got the piece of dg, which is vertical, so that's going to be the vertical side over the hypotenuse, so 4 over 5, because it's a 3, 4, 5 triangle. And the vertical piece of dg, I had guessed dg is in tension, as all of them I guessed in tension, and that means dg looks to be downwards. Downwards means negative in the y direction. And those are all of my y forces. 100 down, 200 up, and the y piece of dg. There they are. Set it equal to 0, and I solve for dg. dg is going to be minus 100 plus 200 times 5, all divided by 4, which is 100 divided by 4, which is 25. 25 times 5 is 125. That's a positive number. Positive means the direction I guessed for dg was correct. In this case, again, I guessed dg in tension away from the joint, so I was right. dg is 125 in tension. All right, so one more equation to go. Now I could do all the x stuff. What are all the x forces? Well, I've got CD to the left, so minus CD. I've got FG to the left, so that's minus the FG, but FG is 150. And then I've got DG to the left, so minus, and DG, but only the x piece. Well, DG is 125, but I only want the x component, so that's times 3 over 5. Makes him the x piece of DG. Those are all the horizontal things. Set this equal to 0, and I solve for CD. So CD is going to be minus 150 minus 125 times 3 over 5. That's minus 150 minus 125 over 5 is 25, and 25 times 3 is 75. So I get minus 225. All right, so CD is minus 225. What does that mean? Well, the negative tells me that the direction I guessed for CD was wrong. I guessed CD to be in tension. I got a negative answer, so that means CD is actually in compression. So CD is 225 in compression. And so we can see, even when I guessed the wrong direction, I will still get the right answer. It's just the direction will be wrong. So it'll be negative instead of positive. So don't take the time, at least for method of sections, to try to figure out what you think. It's more difficult than it is when we're trying to find the reactions. For the reactions, or even when we do method of joints, usually you could use your logic to deduce which direction we think these forces should be in. Here, don't worry about it. Just think everything's in tension. Do the math. If you get a negative answer, you make it compression instead. But this is the method of sections. I've now calculated the force in these three particular members. And what's interesting is we didn't have to find the force in all of these other members. We didn't need AB, we didn't need AH or BH or any of these other things. We didn't calculate any of that. So if we were doing method of joints, in order to get these three answers, we would have been working through this truss little by little, calculating all these different members, all to be able to finally get to the things we actually care about. Which is fine, it works. But we're solving for a bunch of things that we don't need. We're wasting our time. However, if the three members we have of interest happen to be lined up in such a way that we could cut our truss along those three members into two separate pieces, so they're separate independent pieces, Then we could bypass all that stuff and just use one of the pieces of the truss and do global equilibrium on him and figure out our three unknowns from there. Very, very nice technique that lets you save a lot of time if you don't care about the whole truss, you only care about specific parts of the truss. And the other good thing about it is all you're doing is the very first step of all truss analysis we always do every time, which is global equilibrium. We're just doing it again a second time to find out these three external forces because we've broken these members. So now those members are not nice internal forces. They're like external loads now. And we're trying to calculate those external loads. It's like trying to find the reactions all over again. Now, what's nice again also is we could have used this other side over here. We could have done that side and done exactly the same technique. Some of the moments, some of the forces X, some of the forces Y, just like we did here. But for that side of the truss, again, we would assume CD is in tension, DG is in tension, and FG is in tension, which means they go that way this time. And if we do the work for that one, again, we get exactly the same answers. But with the left side, because there was one extra external force, one extra load on that side of the truss, it would have meant there's more stuff going on in these equations over here. Not a big deal for this one extra term, who gives a crap. But if we had a really complicated truss, it might be that one side of the truss has 15 loads and the other side only has one load. And so one side is way easier to solve than the other. But even if not, if they're both the same, then just choose one. It doesn't matter which one you choose. It doesn't have to be the smallest. It doesn't have to be the one with the least number of external loads. It doesn't matter which side you choose. Just choose one. You want to try to use the one that has the least number of external loads just to make your life easier. But you can choose the other one and be perfectly fine as well. All right, so this is method of sections. This is the theory of it. And it's just a secondary technique. If you don't care about the full truss, you only care about particular members. So in this case, we only wanted these three. If you have the ability to cut your truss into two separate pieces by cutting along those members that you want, then method of sections is the best way to handle it. If not, then you're probably using method of joints. And you're just going to have to take the time to find a bunch of members, even if you don't really care about them. All right, so I hope this is helpful. If you have any questions, let me know, and I will see you next time.